So welcome all again. This is week one tutorial for the course Deep Learning. So I'm Pintu Kumar. I'm a PhD scholar at IUR IIT Bombay. So first of all, I think most of you have done a machine learning course, but let's have a recap on a very small recap on machine learning. So the first question is, what actually is machine learning? So if we talk about machine learning in today's concept, machine learning is nothing but what we are trying to learn from data. We are trying to learn some patterns from data. We want to learn some hidden structure in the data, and that is what is machine learning currently. Okay. So based on the type of data that we have, we can classify machine learning into broadly three paradigms. So there can be more divisions, but broadly three subclasses. One is supervised learning, another is unsupervised learning, and last one is reinforcement learning. Okay. So what is supervised learning? So whenever you have data, in data you have some for let's say a data point would look something like x1 comma y1. So x1 is your feature, and this is your associated you can say label or value that you want to predict. Okay. If data exists in this form such that you are given with features as well as the quantity that you want to predict. uh, okay, so Shri Vinayak, there are 4 TAs for this course, and two of them takes class on Saturday 3 to 5, and two of us take class on Tuesday 6 to 8, the current time slot. So every week, no matter holiday or whatever, these sessions will be held on these times only. Yeah, that's what you asked. Okay. So I was talking about what is supervised learning. So if you have data where you are given with feature as well as the quantity that you want to predict, okay, and you learn on these kind of data, then the setup is called your supervised learning. For example, let's say for past 10 years, you are given on every day the temperature, humidity, and yeah, you are given these two quantities, and you are given whether it, so this is your x, that is temperature and humidity, and you are also given with yi, that is whether it rained on that day or not, rain or no rain. Okay. So because you are given yi is also along with your xi, so this kind of setups fall into something called as supervised learning. So here your task would be given some temperature and humidity level for some future day. You want to predict whether it would rain on that day or not. Okay. So this supervised learning can further be subdivided into two classes. One is called classification and one is called regression. Okay. So what is classification? In classification, these yi's that I mentioned are discrete values. Okay. So by discrete value, I mean that like they have gaps in between the numerical values. For example, whether it would rain or not rain. So we can represent rain by 1 and not rain by 0. Okay. So another subdivision of supervised learning is something that is called regression. In regression, your yi's are continuous in nature. Okay. For example, let's say in this example only, this rain or not rain was also your feature. Okay. This was part of your x, and you want to predict amount of rain on that particular day. Okay. So now amount of rain that you will experience on certain day, that would be a continuous quantity, right? So yeah, let me admit this person. Yeah. So that would be a continuous quantity. So if you want to train a model that should predict the amount of rain, that would fall into the category of regression models. Okay. So again, a very small recap. Supervised learning is something in which you have x as well as the associated label or the value that you want to predict available with you, and that can be divided into two classes. One is classification, where your y is discrete value, for example 0, 1, 2. Okay. And in regression, your y's are a continuous value. Okay. The second regime is something that is called as unsupervised learning. Okay. So unsupervised learning means that you have only features available with you. Okay. So there is no yi available with you. So let's say this is your some R2 space. You just have points in this. Okay. Let's say something like this. So these are your points. Now you can clearly see that there are two clusters of data points. Okay. But you are not explicitly given that this particular cluster belongs to some class and this particular cluster belongs to some class. So if you want to learn an algorithm that can cluster your data, that would fall into something that is called as unsupervised learning. So clustering is an example of unsupervised learning. Okay. Last one is something that is called reinforcement learning. So reinforcement learning is like, I would give you an example. Example is a self-driving car or a drone that you can fly. Okay. So what happens in a self-driving car? After every step, you have to take some action. Action would be if you want to increase the speed or decrease the speed, or you want to apply the brake, or you want to take a turn. Okay. So on every step, you will take some action. Based on that action, your environment will change around you. So if you increase your speed or decrease your speed, based on that, your environment will change around you. And now again in the new environment, you will take some action. Okay. So this is the framework of reinforcement learning. Now, how do we train these kind of models? To train these kind of models, we accumulate rewards that we get on every step, and maximizing that reward, we are able to train these kind of agents or models. Okay. Any doubt till this point? We talked about supervised learning, unsupervised learning, and reinforcement learning. Any doubt till this point? Okay, thank you, Naman. Okay, so now this course is not on machine learning, but on reinforcement learning. Oh, sorry, deep learning. Yeah, somebody has raised his hand, I guess. Okay, okay, he said no. Okay, so this course is not on machine learning, but deep learning. So why I wanted to tell you these topics is, these days, deep learning is being used to solve all kind of problems, right? So you will find deep, okay. Am I now audible to you guys? I think there was some internet disruption from my side. I hope I'm audible now. There was some internet issue from my side. Okay. My screen is visible. The mobile internet is not working that great. There is some internet issue in the institute. I'll go to try. Yeah. Okay. Screen is visible now. Okay, I'll continue. Sorry for the break. Okay. So why I mentioned these topics, these days, if you look at supervised learning or unsupervised learning or even RL frameworks, most of the models that are being used are based on deep learning methods. Okay. So actually what does deep learning mean is that you will stack lot of perceptrons together to get your desired output. What are perceptron? You might have covered in week 1 and we'll also have a look at it in a few moments. Before that, we can just try these simple examples so that in our minds we are clear what setup, what problems we are tackling. Okay. So the first question is, which of these is not a supervised learning? So can someone please type which of these do you think is not a supervised learning? Yeah, somebody typed clustering and that's correct. In classification, you need X as well as Y, the label where you need to classify. In regression also, you need feature as well as the value that you want to predict. In clustering, you don't need any of the Ys. Okay, so clustering is the correct answer. Okay, so second question is, uh, you are given review of few movies, mark positive, negative, and neutral. Classify these reviews. So you want to train a model that can classify these reviews for new movie. Okay. So what kind of setup is this? Is this supervised learning, semi-supervised learning, unsupervised learning, or reinforcement learning? Okay. So yeah, this is supervised learning because you have movies, that is your feature. Okay. And you have ratings available, that is your label. So this is supervised learning. What is semi-supervised learning? The term coined. So I will tell you. So in semi-supervised learning, you have some small amount of labeled data, okay, and you have some large amount of unlabeled data, and you want to use both of them to learn. So those kind of setup would fall into so this kind of combination would fall into something called as semi-supervised learning. Okay. Okay, let's go to the next question. These are some easy questions. Okay. The selling price of a house depends on following factors. It depends on number of bedrooms, number of kitchens, number of bathrooms, the year in which the house was built, and the square foot, the area on which it is built. So we want to predict the selling price of the house, what kind of task it is. Okay. So options are binary classification, multi-level classification, simple linear regression, or multiple linear regression. Okay. So if you look at the selling price of a house, these are not some fixed discrete quantities. You can have a selling price of a house as let's say 1.5 million, or you can have 1.501 million. So these are the continuous values that price can take. So first of all, this is a linear regression or regression for let's say, okay. No, Manas, it is not a classification problem because the values that we want to predict are continuous in nature. They are not discrete. Okay. So, yeah. So this is linear regression, and we want to predict only one value. That is, we want to predict only selling price of the house. That's why it is simple linear regression. In multiple linear regression, you would have got more than one output. Okay, probably stacked together. Okay. So, okay, now there is one more thing that is here. What is binary classification and what is a multi-level classification? So in classification, if you want to classify your Y only among the two choices that you have, it can be either 0 or 1, it can be -1 or 1. Though that setup is called binary classification. If your Y belongs to a larger set, let's say it can be 0, 1, 2, or let's say your Y is either cat, dog, or let's say tiger. You want to train a model such that if you give a photo to your model, it can tell you whether it is a photo of a cat or a dog or a tiger. So you have more than two labels, then that setup is called multi-class classification. Okay. Manas, I hope it is clear that it is not multi-class classification, but simple linear regression. Okay. Okay, so here is one more question. So the question says, imagine a newly born starts to learn walking. People are joining. Let me admit them. Yeah. So imagine a newly born starts to learn walking.
Sir,
It will try.
can you please explain the multiple linear regression again?
Can you please repeat the question?
Sir, can you explain the multiple linear regression again?
Okay. So in your simple linear regression, the quantity of interest that you have is a single output vector that you have, right? In multiple linear regression, the
Yes.
quantity of interest is not single, but multiple outputs that you want to train your model for. Okay.
Okay, sir.
So yeah. So the next question is, imagine a newly born starts to learn walking. It will try to find suitable policy to learn walking. After repeated falling and getting up, specify what type of machine learning algorithm is best suited to do the same. Okay. So the child would start walking. If he's able to keep standing, then he will feel that he has got rewarded because he's able to stand. Let's say if he is able to make a step, then he will feel that he has got some reward. Every time he will fall, he will think that he has got some kind of punishment, okay, or negative reward. So this is how a child sort of learns to walk or do different kind of things when he is young. So similar, so reinforcement learning is motivated from similar kind of setup, and this would fall into setup reinforcement learning. Any doubt till this point? Then we'll go to whatever was. So this was sort of recap for machine learning and the setup. So any doubt till now so that we can move ahead? Okay, thank you. So now whatever was covered in week 1 of this course, so those both of them were so there were two types of neuron that were talked about. Both of them were classification setup. So right now what we are trying to do is classification, that is supervised learning setup and classification. Also the classification that we are trying to do right now is just binary classification, right? Okay. So this is what we are trying to do right now. Okay. So these are some very old models, but this is very essential for understanding how a deep learning model works. Right now, okay. So if any one of you might have seen, I think most of you would have. So this model look like. So in today's lecture or whatever was covered in week 1, we are just trying to focus. Okay. So this is the focus of discussion from now on. So you need not raise your hand. You can straight away unmute and speak. Yeah, whoever has raised hand.
Sir, sir, your voice is breaking, sir.
Is it breaking for everyone? Can someone please confirm?
Yes.
No, sir.
No,
Yes, sir.
sir,
Yes, sir.
your
No,
voice
sir.
is
You are
clear.
clear. No, sir. Your voice is breaking, sir.
Okay, now is it
Yeah,
better?
it's
No,
breaking.
sir.
Yes.
Okay, I'll try to keep it
Yes, sir.
Yes,
close to
yes.
my mouth. Okay. Okay. So, okay, thank you for letting me know.
Okay, sir.
Okay, so this is called something as MP neuron. Okay, so this was one of the first neural model that was proposed, that was motivated by a biological neuron that is covered very beautifully in the course. So yeah, so how does MP neuron looks like? So these X1, X2, X3, X4 that you see on the left, these are inputs to your neuron. Okay, this is your neuron. This circular thing is your neuron, and this x1, x2, x3, x4 is your input to the neuron. And based on the input, it will produce some y. So this y is output of this neuron. Okay, right now what we are assuming is that all these x1, x2, x3, x4 are just binary features. Binary means that they are either 0 or 1. And the output is also binary, 0 or 1. Okay, so now what does this MP neuron do? Okay, so it will take sum of all these inputs that it has received. Okay, so it will do x1 plus x2 plus x3 plus x4. And based on this value of this sum, it will decide whether my y is 0 or 1. So if this sum is greater than equal to some theta, this theta is to be decided by you based on your application. Okay. If this sum is greater than theta, then you say that your y is equal to 1. Otherwise, if this is strictly less than theta, you will say that your y is 0. Okay, this is how this MP neuron was proposed. So based on some feature, you had to decide what is the value of your theta, and you can use it for some predictions later on. Okay, so okay, this is a question that was in previous year's assignment based on this. So the question says, suppose that we have a Boolean function that takes in 5 input. So we have a, so this is related to MP neuron also only, that is written in the last. So we have 5 inputs, 1, 2, 3, 4, 5, x1, x2, x3, x4, x5. Now it says that we have theta is equal to 1. So how does this MP neuron works? That if my x1 plus x2 plus x3 plus x4 plus x5, if this is greater than equal to 1, then my y is 1. Okay. Otherwise, my y is 0. Okay. This is how this MP neuron works. So it is asking for how many inputs is my output y is equal to 1. Okay. Okay. So one thing that you should see is, like, you guys can try for 1 minute, then I'll give the answer. If anybody, one of you knows, you can type it in the chat box. Then I'll solve this question. But till that time, if anybody wants to try, you can solve and give me the answer. Like if we have an MP neuron of this setup, it is asking how many inputs will give output y is equal to 1. Okay, I think that is correct, but we will
31.
solve. Yeah, that is correct, but we'll solve for others also. Okay, so now let's see
2 raised
what are
to 5.
Himanshi, you will have the recorded session after 8, but I think right now NPTEL team has not shared the sheet for the recordings. So I think the first recording would go 2-3 days late. From the next week onwards, if the session ends at 8, I think mostly till 8:30 or 8:45, I'll upload the recordings and everything. Okay. Okay. So let's get back to the question. Uh, yeah. So we have 5 inputs. So there is 5 entry points to this neuron. So each of them has 2 choices. So first one has 2 choices, second one has 2 choices, and so on. So the total number of possible inputs is 2 to the power 5. Okay. So if you take all the possible combinations of 1 and 0, let's say 1, 1, 1, 1, 1, 1, 0, 1, 0, 1. These are inputs to your neuron, right? So if you count them, you will have 2 to the 5 number of total inputs possible. Okay. Okay. So me. Am I audible now?
Yes.
Okay, I'll change my earphone for the next time probably. Right now I don't have any other, but I'll change this for the next time. Okay. So yeah, what I was saying is that we have 32 possible inputs for this MP neuron. Okay, because we have five places to fill. Now my theta value is 1. Okay, so when will this sum will be greater than equal to 1? If even one of them is 1, then my sum will be always greater than equal to 1. Okay, so the only case when my y is not equal to 1, y is equal to 0, only if all my x1, x2, x3, x4, x5 is 0. Only in this situation, this sum will be strictly less than 1. Okay. So for all other situations, my y will be 1. Okay. So we will subtract one choice where we have y is equal to 0. So we have 31 inputs for which y is equal to 1. Okay. 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 So one more small thing. This is not very used, but this was covered in the lecture, and there are questions based on this also in the assignment. So I'll cover this question. Okay. So these features that sorry, these features that we talked about, that is x1, x2, and x5 that we had in previous example. So these features can be of two types. It can be either inhibitory or excitatory. Okay. So what inhibitory features mean is, if my inhibitory feature is positive, okay, then my y will always be 0. Okay. No matter what other features are, if my inhibitory feature is 1, then my y is 0. I'll take an example, the same example that professor took in the course. Let's say you want to go and watch a movie. Okay. So let's say you want have featured something like who is the actor, who is the director, and other option can be whether you are ill or not today. Okay. So no matter what actor and director is, let's say if you are ill today, okay, then you won't go to a theater and watch a movie, right? So if you're then your this feature x3, that is you are ill or not, this becomes a inhibitory feature. So if your inhibitory feature is 1, then no matter what other values are, you will always get your y is equal to 0. Okay. So here is an example. Any doubt in this?
No,
I
sir.
hope no. Okay. So here is a simple example. So yeah. So given a MP neuron, again your neuron is again MP neuron. Okay. So given an MP neuron, let's say it has three inputs. Now this has three inputs, x1, x2, x3. And this one, x3 is an inhibitory feature. So we can denote it like this. Okay. So for the input 110, what is the value of y? Okay. So what is the value of y? So your inhibitory feature right now is 0. Okay. So we will take sum of these values then, x1 plus x2 plus x3, and this is 2. If my 2 is greater than equal to theta, then my y will be 1. If it is strictly less than theta, then my y is equal to 0. For this input, based on theta, we can decide whether y is 1 or 0. Now, if we look at second input, this is 1, 1, 1. Now my inhibitory feature, that is x3, is 1. Okay. So this would simply mean that my y is equal to 0. Okay. No matter what other values are, even if you look, the first two values in both the inputs are exactly the same. But just because of the last entry, my y can change. Okay. Yeah, Viren, that was correct answer. Okay. so this question is also similar to one in the assignment. This is not exactly the same question, but similar to what is there in your assignment. So there is an MP neuron for the AND Boolean function. So this is x1 plus x2 plus x3 is greater than or equal to 1. So your theta is given to be 1 over here. So you have to take the correct options among these. Okay. Okay, so I'll give you a minute. You give it a thought. Which of these you think is correct? I will tell you the answer, then it is better that you think about it and then it would be more clear to you. These are easy questions. I'm not sure. I haven't solved, but I don't think all would be correct. We'll see. Okay. Okay. We have couple of answers, so let's see. So the first one is the input is 0, 1, and 1. Okay. Yeah. So, so the sum is 2 over here, which is strictly greater than 1. So my y should be 1. And it says y is equal to 1 for this input. So this one is correct. Okay. If we look at second one, the sum is again 1, which is again 1 is greater than or equal to 1 is true. So my y should be 1 over here. But we're given that y is equal to 0 for this particular input. So this is not correct. Okay. Ravichandran, so the second option is not correct at least. For the third one, the sum is 3, which is greater than or equal to 1. So y again is 1. So this option is again correct. For the last one, again sum is 1, which is greater than or equal to 1. And for this, y should also be again be 1. So this is again incorrect. And yeah, this should be y is equal to 1. I don't think this is AND Boolean function. This is incorrectly written over here. This should be OR Boolean function. Okay.
Yes.
This doesn't match over here. So yeah, probably some typo here. Okay. So this was MP neuron. Okay. So these are not being used as of current deep learning models. So what is being used as component of current deep learning model is something known as perceptron. Okay. So another name for our deep learning models is multi-layer perceptron. Some of you might know. Okay. So if you understand perceptron, you just need to take multiple layers of it and you'll get deep learning. Okay. So yeah, deep learning models. Okay. So right now I'm talking about very simple perceptron, but I'll just motivate you, okay, for a more complex kind of perceptron that we'll cover in the next week, but I'll just motivate you. Okay. So in MP neuron, we were just taking summation xis. Okay. So there is a possibility that some features might be important to you and some features might not be important to you. Okay, let's say uh, mm, you collect data of candidates and you want to hire someone. Okay, now you don't want to go through manual interview process. What you want to do is that candidates fill their everything, name and whatever qualification they have and everything, and your machine learning algorithm should automatically tell you whether you should hire that person or not. Okay, at least it should give you some idea whether you should hire that person or not. Okay, now the features that you collected, let's say name, okay, gender, these features don't make any sense when you hire a person or you don't hire a person. Okay, name and gender are irrelevant over there. And some features, let's say for example qualification of that person, okay, or experience of that person, these are of high importance to you. Okay, qualification or experience. So rather than taking a simple sum of x's, let's say if you give these 0 weights, okay, and if you give these very high weights, that is you multiply these numbers by 0, 0 times name plus 0 times gender plus 0.8 times, let's say, qualification, and then you obtain this sum. That is called as weighted sum. Okay, and that I have motivated by an example that this is very much practical, that we should take weighted sum of these features. Okay, so rather than taking just the sum, if you take the weighted sum of these inputs that you had, then you got something that is called as perceptron. Okay, and again, these are your inputs, your y is your output, and before outputting, what you do, okay, so one thing is that if you have done machine learning course, then you will appreciate this thing, is that in classification, I'll just take a small detour so that it is more clear to you. Okay, just give me a second. So what happens in classification? Uh, you have some data points, let's say, of two types with you. Right now, we are just talking about binary classification. Okay, and you want to separate these two data. Okay, so if you draw this line, you can clearly see that on one side of this line is your one type of data, and on another side of your line is another type of data. Okay, so right now you are able to separate it via a linear line. Okay, so these kind of classifiers that are linear in nature are known as linear classifier. Okay, but these linear classifier, if you talk about real world data, are not very powerful. Okay, in their like true sense. Okay, like if you are just trying to draw lines, let's say, I'll take a very again a small example that would be very clear to you. Okay, so let's say this is your another type of data point where you have these two types of point, that is cross and circle. You can clearly see that if you draw a boundary like this, then this boundary separates these two data points. You can make a rule that if my point is within this boundary, then you classify it as a circle. If it is outside this boundary, then classify it as cross, right? But you can't do this with linear classifiers. You can't draw a straight line to separate these two kind of data points. Okay, so in their true form, I'm again focusing on the word true form because linear classifiers can be modified to non-linear classifiers. So in their true form, linear classifier are not very powerful. Okay, so for perceptron also, this quantity that we obtained, wixi, this would create a linear classifier only. So we can pass this linear quantity that we have obtained through some non-linear function f. What are the possible non-linear functions? What we can do with them? That we'll see in next week content. But today, let's say that this is possible, that we can convert this our non-linear this linear quantity into non-linear quantity by passing it through some non-linear function. Okay, so again, back to the story. So in MP neuron, you only had some x1, x2, x3, x4. Now we have a possibility of summation wixi. Okay, and we again threshold it on theta. If my sum is greater than equal to theta, then I'll take y is equal to 1. If it is strictly less than theta, then I'll take 0. Okay, one small advantage that we have over here is we can rewrite is, so if we take this theta to this side, okay, so we can rewrite it as I is equal to 1 to n wixi minus theta is greater than equal to 0. Okay, so here I have just taken the summation from 0 to n rather than 1 to n, and this theta is included over here. So if you look, my w0 is nothing but minus of theta, and x0 is nothing but 1 in this summation. Then I can threshold at 0. Okay, and another interesting thing that happened over here is, because I was able to push theta in my summation, now one thing that I can do is that I can learn this theta also. Okay, and I can learn these weights as well. By learning, I mean that if we have some previous data available with us, we will pick those values of weights and theta such that my model or the perceptron makes minimum error. Okay. Yeah. Anybody has anything to say? Bhavesh Kumar, you have anything to say? You are unmuted.
No, no, no. By mistake, it has been unmuted.
Okay,
Sorry.
that's perfectly fine.
Sir, I have a question.
Ah, sure.
Sir, how can we learn the theta? I can understand that.
Okay, how will we learn that theta? Okay. So I'll request you to wait for next 5-7 minutes. We'll see how will we learn theta. Okay. And one thing that I can say right now is, so in machine learning, what we do is, based on the previous data that we have, we try to learn all these WIs, and that would also include theta. And how do we learn that? Right now we'll see. Okay.
Okay.
Okay, this is the very next step. Okay. So how will we learn this theta is written over here. We'll see how we learn theta. Let's say initially you can randomize your W. So your W includes minus theta as well as the W1, W2, Wn. I won't write it in this form again. I'll just consider it as W. Okay, so if I say that we are updating W, that means we are updating weights as well as that particular theta that we had. Okay, so let's say, okay, so in classification, as I said that we have some crosses and we have some circles. Now, when we want to do something more mathematically grounded, we can replace this notation by, so for all the crosses, we say that they belong to class 1, and for all the circles, we say that it belongs to class 0. Okay, this is one notation. Another notation that is very common is that for all crosses, you can say it belongs to class 1, and circle belongs to class -1. Okay, this is another very common notation. Or we can say that this belongs to class positive and this belongs to class negative. Okay, so class positive means it is one type of data point, and class negative means that it is another type of data point. Okay, so if my point is positive, okay, okay, so just one more small thing. So uh, why do we want to update our theta or these things? This should be clear. So why do we want to update this is, so we have some previous data points available with us. Let's say we have x1 comma y1, so on till xn comma yn. And when we initialize this randomly, then our perceptron was making some error on these kind of data points. That means when we were giving it, let's say x1, it was not giving out the correct y1. Okay, so we want to find that particular value of w and theta so that it gives correct prediction on these data points. Okay, okay, so this is my update condition, that if my point was from a positive class, that is it was 1, if my y is equal to 1 for this particular point, and there is a misclassification of this point. So if it would have been correctly classified, that would have meant that W transpose X is greater than 0. Now this notation uh, W transpose X means summation I is equal to 0 to n Wi xi. This is just the dot product of W and xi. This is just the notation. So this quantity is W transpose X. Okay. Like if you will go ahead in deep learning, this is the notation that people are going to use. They would never write explicit summation. Okay. So if my W transpose X is greater than equal to 0, then okay, so if my W transpose X is less than 0, that is we are making error at the point X, then I'll update my W to be W plus X. Okay. If my point was negative, that is the output should have been -1, but the output is being getting out as W transpose X is greater than 0. So then what I'll do is I'll update my W as W is equal to W minus X. This is what I'm gonna do. Okay, so whoever asked how do we update, just hold for a minute or two more, then it would be much more clearer to you. Okay, so this is the update condition that we'll be using. Okay, okay, one more thing that is important. So this is an introductory week, so things are in bits and pieces, not very connected, but it will help you in future. Things will be more clear and more connected. Okay. So there is something that is called as linear separability. Okay. This is a property of data points. So this is a property that is associated with data points and not with your models. Okay. So I'll take a very simple separability, two-dimensional example. Okay. Studious amateur wants to join. Okay. Dr. Parivan. Okay. Let's say you have two kinds of data point. Okay. This is 1 and 0. And linear separability means, so if your data is in two dimension, okay, if you can separate it via a line, okay, then your data set is linearly separable. Okay, this is the simple explanation. This is the definition for linear separability. If your data is in two dimension and you can separate it by a one dimensional line, the line is one dimensional, then it is called linearly separable. Your data set is called linearly separable. Okay. Uh, so if it was a one dimensional data set, okay, so let's say there is a one over here, one over here, zero over here, one over here again. So this is a two-dimensional, sorry, one-dimensional line. So if you were able to separate it via some point, so after which there are all ones and after which there are all zeros, before which there are all zeros, then it would have been linearly separable. But if you look at this example, this data set that is available to us is not linearly separable. Okay. Whereas this data point is linearly separable. This is a basic intuition. Now, if we look at the real world data set that we encounter in our real life that we actually want to process, they actually are a much higher dimension data set than two-dimensional data set. Okay. So let's say if we had three-dimensional data set, then we would have said that if it is separable by a two-dimensional plane, so on one side of a plane you have all the positive points, on other side you have all the negative points, then that data point is linearly separable. So if you have some n-dimensional data points, this is Rn cross R. So if you have some n-dimensional data points, and if they can be separated out by n minus 1 dimensional hyperplane, so the word hyperplane is nothing but an extension of plane. Okay, for example, if you have one dimensional line, you can divide it by a point in two half. If you have a two-dimensional plane, then you can divide that two-dimensional plane via some line. If you have a three-dimension thing, then you can divide this thing via some plane. So you can't imagine it in fourth dimension, but the extension of this in higher dimension is called hyperplane. Okay. So if you have n-dimensional data and you are able to partition it into two parts using n minus 1 dimensional hyperplane, so that on one part you have all the positive points, on the other half you have all the negative points, then that kind of data is called linearly separable data. Okay. This is one thing. And mathematically, if somebody asks you to write how can you say whether a data set is linearly separable or not? So one very small thing before we move ahead. This next thing that I'm going to say is very important and might give you a lot of intuitions. Okay. So let's say, I would request you to please slightly focus. This is my two-dimensional plane. Okay. And I want to draw a line. So how can you represent a line on a two-dimensional plane? One thing is that you can write an equation of this form. Okay, let's say x plus y is equal to 1, or yeah, or you can just, let's take a very more simpler, x plus y is equal to 0. Okay, so how does this line looks? This would look like, this is x is equal to minus y. So this would look something like this if I'm not wrong, right? This is one way of denoting a line, right? You can write it in form of equations. Another way to represent a line is via its normal vector. Okay, what is its normal vector? If you look at the line and you draw a perpendicular at your 0, so whatever vector you get over here, that is called its normal vector. So if you just write the normal vector of that particular line, that can also be used to uniquely characterize the line. Okay, so this line x plus y is given by this, x plus y is equal to 0 is given by this particular red vector. Okay, now what is this vector? How can you obtain from equation of your line is that if you just take the coefficients of x and y's, whatever you have, so you take 1 comma 1, this is exactly the red vector that we were showing. If you look, this was at negative 45 degree. So a 90-degree angle would look like something that is at 45 degree from it. So this is exactly your vector 1 comma 1, right? So this is what I wanted to bring to your notice, that yeah. So you can represent a line in both the ways. Okay. Also, now from here on, one more thing. So if you have some arbitrary, let's say x and y, let's say x1, y1, that lies on this line. Okay. Let's say this particular point lies on this line. What would this satisfy? That my x1 plus y1 is 0. If you write it slightly more formally, this is 1, 1, and this is x1, y1. So if you look at it carefully, what we are doing over here is nothing but we are taking the dot product of 1, 1 with x1, y1, right? So what I mean to say over here is that for any point on this line, dot product of this line, the dot product of this point with this particular vector is always 0. Okay. So if you have a line, the dot product of that particular line, points on that line, along with this red vector that is the perpendicular vector, is always 0. Okay. So for example, I'll take just one more example. That is, let's say you have line 2x plus 3y is equal to 0. Then its perpendicular vector would look like something like 2 comma 3. Let's call it w. Then for all the points on that particular line, let's say if you have x comma y on line, then w dot product, so this transpose means dot product with this xy is 0. Okay, this is one thing that I wanted to say. Now one more small thing. So if you have this particular line and your this perpendicular vector is telling is towards this direction. Okay, so if you have a line on 2D, you will have two halves of that line. So this is one half, this is the second half. So if your arrow is pointing towards this half, then for this particular half, if you take any point, let's say this point is x star comma y star, then your w transpose with x star and y star is going to be greater than, strictly greater than 0. If you are taking any point on the right hand side, or I would say the in the direction of your normal vector. And similarly, if you take a point on the other side, then for this w transpose x is strictly less than 0. This is what happens in 2 dimension. Any doubt in this? This was slightly lengthy and I might not be very clear here. Any doubt in this? So just a summary that uh, just yes, I'll take it on every Tuesday. There are other TAs also who are taking similar session. So you can join their session and like whichever session you want to attend and is useful for you, you can attend those sessions. These will be held weekly. Okay. So just there were many things that I was saying. So just a small thing. So let's say if you have a line ax plus by is equal to 0, then if you take a normal vector to this particular line, yes, recording will also be shared. First recording might take 1 or 2 days. Later on, it will be shared like instantly almost. Okay. So let's say if your equation of line is ax plus by is equal to 0. Okay. And if you take a normal vector on this line, then that normal vector w is nothing but your a comma b. That is coefficient of your line. Okay. So this is the first thing that I said, that for every line you have a corresponding w that is nothing but coefficient of your x and y. Himanshi, I didn't take a class on 27 December. That was some other TA. This is the first class that I'm taking today. Okay. Okay. So the w is a comma b. This is the first thing that I said. Okay. Now let's say if I have point x1 comma y1 that lies on the line. The second thing that I said is that w transpose with x1 y1, that is the dot product of w L with any point that lies on the line is always 0. This is the second thing that I said. Third thing is that w transpose, let's say I have a point x2 comma y2 which is in the half that is pointing towards this vector w. Okay, the w is pointing in this direction and the point is also in that particular half only. Then w transpose x2 comma y2 is strictly greater than 0. Fourth point is if there is like a point x3 comma y3 that is in the other half, then this is strictly less than 0. Okay. Yeah. This is the geometry of a line in 2D. Okay. This similar thing can be extended in higher dimensions. So if you have a plane now, I'll just take a very small time. Yeah, I think this is useful to understand the whole classification itself. So I am devoting some time towards it. It was not done, I know, but I think it is useful for you. Okay, so let's say we have some plane. How does equation of a plane look like? So equation of a plane would look like 3x plus 3y plus 4z is equal to 0, let's say. This is an example of a equation of a plane. Okay, then your w would become 2, 3 and 4. And again, all the 4 points that I mentioned just now would hold. That if the a point lies on the plane, then the dot product with w would be 0. If it is on the half towards which the arrow would be pointing, the normal vector would be pointing, then it would be greater than 0 and it would be less than 0. And similarly, you can extend this definition to n-dimensional spaces. Okay. So now we will get back to the definition of linear separability. So if you have some uh, let's say r n-dimensional data, for example here you had 2-dimensional data, then you want to separate it via a n minus 1 dimensional hyperplane. Here you wanted to separate it via 1-dimensional line. Okay, so to represent a 1-dimensional line you needed a vector that had 2 components in it. So w had 2 components. Okay, so to represent an n-dimensional one hyperplane you need a vector w that has n components in it. Okay, so this is the hyperplane that will separate the plane in two half, and for all the points that are from positive class that would lie on one side of the plane. So for them, W transpose Xi would be greater than equal to 0. That is, they are on one half of the plane, and for others, it is strictly less than 0 for negatively points. So these kinds of data sets are called linearly separable data points. Okay. Okay.
Sir, greater than equal to?
Okay. So yeah, I have taken greater than equal to for a reason, is that the professor who is teaching is using greater than equal to. So you can take this equal to either here or here, but you need to take it at one place only. Okay. So let's say you want to separate your plane in two half. Now, if you just take this, okay, if you want to separate it into two half, if you just take points here and here, then what happens to the points on the line? Okay, so should we assign it to positive class or should we assign it to negative class? So this is just by our choice that we have assigned this also to positive class only. Okay. That's why we have taken greater than equal to over here, that the points on the hyperplane would also belong to positive class. Okay. Okay. So why I did linear separability? The reason for that is you saw this update condition over here. Okay. When we are talking about perceptron, we had some update condition on the value of our W as well as our theta. Please don't confuse this W with the line. Actually, they are same, but now I'm talking about the W, uh, the weights of this particular perceptron. They would be same, but yeah. Okay. Now we have constructed some update condition for our W, but if my update condition don't give me desired result, what is the use of it? Okay. So the question is whether this perceptron update step is useful or not. Okay. So the answer is that it is useful. So if my data set is finite and linearly separable, okay, then whatever update condition I have written, that will converge in some finite step. Somebody has unmuted. If you have any question, you can ask. Okay, that's fine. Okay, so the condition is that if it is finite and linearly separable, then it will converge in finite number of steps. Now, one thing I would like to say, whenever you will have a real life data set, there is a 99% chance that the data set that you will get is not linearly separable. So how do we tackle data set that are not linearly separable? That we'll do in further in this course in next week or onwards. So for today, the algorithm that we are doing, that is only for linearly separable data, and this is the update condition that we mentioned about the perceptron. Okay. So let's try looking at some questions related to it. Then I'll also try to elaborately answer one of the question that was asked, like how do we know, like how do we update theta, or how do we learn theta? That one way was, okay, so you want to know what do we mean by converge, or yeah, okay, I'll tell you. So if you want me to prove the convergence, I am not planning to prove the convergence, because I looked at the lecture that was there on NPTEL, and I think that proof is more than enough. Like there is nothing for me to add. If somebody has not understood the proof, just go through that again, and I think that would be easy for you to follow. That is not very difficult. But I'll tell you what it means to converge. Okay. So okay, first I will talk generally from perspective of machine learning and deep learning. Then I'll talk specific about perceptron. Okay. So in machine learning also, you initialize some weight W. Okay. And then you keep updating this W. Okay. So your W is W1, W2. You keep getting new weights. Okay. So this W1 Okay, I'll change the notation. So you get one set of weight, that is your W1, then you get some W2, and you keep updating it until you converge. People say that until you converge. Okay. So in machine learning or deep learning, convergence can have two or three meanings. Okay. First is that your W, so for some particular W, your loss function has become 0. Okay, so the loss that you are making has become 0. So whatever training data points you had, you are able to learn a W for which all the predictions on this training data set is correct. Okay, so in real life this would be very rare, and in many situations you won't want it to happen. That we'll see why. But yeah, one definition of convergence is that your loss function is 0. Okay. Another thing is that you're making updates. Let's say you have WK and you have WK plus 1. You went from WK to WK plus 1, but there is no change. So your WK and WK plus 1 is exactly the same. So you are not making any further improvement. Then also we can say that our algorithm has sort of converged. I'll come to the convergence, what is meant by convergence here. Right now I'm just talking in general machine learning sense. Just remember this. Okay, this is the second way. Third thing that we can do is, let's say we have some loss function, right? So let's say from WK you reached at WK plus 1. Okay, so you made okay, this is not equal to, you reached from WK to WK plus 1. You made some change in WK, but your loss remained same. So even when you updated from WK to WK plus 1, your loss didn't change. So even if you further update, then your loss is not going to change. If you're sure about this, then you can stop your algorithm and you can say that we have sort of converged. Okay, this is what we mean in by convergence or training in machine learning. Okay, now if we talk in terms of perceptron, convergence means, now I'm talking in terms of perceptron. Okay, so convergence means that you will find such a W star so that uh, you are making 0 error on training data. Okay, so that means that whatever values of W1, W2, W3, W4 and minus theta you have reached, for that particular value if you use, then there is no misclassification. Okay, I hope I'm clear what I mean by convergence. Shri Vinayak, I hope I'm clear. I was able to answer it. Okay. Okay, so this is a question that is again from previous year's assignment. So this says that a table shows the temperature and humidity data for two cities. Is the data linearly separable? Okay, so first of all we should identify what is our x and what is our label. Okay, so temperature and humidity is my x, these two combined will form my x, and the city is my label. Okay, so now we have two labels, A and D. Okay, now we can talk about linear separability. So the only thing that you need to do is you just need to plot, because this is just two-dimensional data, you need to plot and see whether this is linearly separable or not. Okay, so even before plotting we can see this is linearly separable because one of the quantity is minus 28. So let's try to plot. This is 2550. So x, let's say, represents temperature and y represents humidity. So x is 25 and y is some 50. So this is for point A. This is 20 and 60. This is also some A. This is 30 and 40. This is also some A. Okay. Now B is minus 28 and 45. So this is, let's say, D. So can you separate A and D via some line? Yeah, there are many lines via which you can separate. You can choose this line, you can choose this line, you can choose this line. So these are linearly separate. Again, one more interesting question that you might have covered in machine learning is, what is the best fit line? Okay, so there are some answers to it if you go through SVM or those kind of things. They try to quantify which line is the best line. So again, that is a different question. Okay, so this is an interesting question. So yeah, so which of the following Boolean functions cannot be implemented via perceptron? Okay, so what can be, yeah, XOR is correct, whoever said that. So what are the functions that can be implemented via perceptron? Only those which are finite and linearly separable. So Boolean functions will always be finite because they have only two inputs, right? So those will be finite. We just need to check whether these are linearly separable or not. Okay. So let's try to draw all four of them. Okay. So yeah. Okay. So now what does AND do? 0 and 0 is 0. So I'll write 0 over here. For AND, 1 and 0 is also 0. So this is also 0. This point will also be 0. And 1 and 1 is 1. So this will be 1. So can we separate them via a line? Yes, we can draw a line over here and we can very well separate them. Let's look at another, that is OR. So for OR, 0 and 0 is 0. 1 and 0 is 1. This is also 1. This is 1. Again, can we separate it? Yes, we can draw a line over here and we can separate these data points. So we can learn these functions via perceptron. Third one is XOR. Okay. So what is 0 XOR 1? So in XOR, if one of them is 1, then you'll get 1. If both of them are 1, then you'll get 0. And if none of them is, so I'll draw the table for XOR. So this is, let's say A, this is B, this is A XOR B. I think I'm drawing correctly. I'll make this table correctly. 0, 0, 0, 1, 1, 0, 1, 1. So this is 0, this is 1, 1, 0. Okay, this is how XOR operation looks like. Okay, so just a second, somebody is joining. I'll admit and yeah. Okay, so now if we write this thing, this is 0, 0 is 0, this is 1, this is 1, and this is again 0. Now, no matter what line you choose, you can't separate this 1 and 0 via some linear plane or a line. That's why this XOR can't be implemented via Boolean functions. Okay, so this is what motivated people to go for multi-layer perceptron. Okay, so I'm not sure whether you joined late, but we did perceptron in very much detail. So I'll just try to again introduce it for you. This would be brief for others, sorry. So a perceptron is a, let's say, this circular thing that will have input x1, x2, x3, x4 along with some weights w1, w2, w3, w4 that will give some output y. Okay. So so how would this output be given? That would depend on this particular rule, that if my summation of wi xi is greater than equal to 0, then my y is 1, and if it is less than 0, then it is 0. Okay, this is what is meant by perceptron. And these w1, w2, w3, w4 is learned by some update rule that was mentioned, that if you are at a positive point and you are making some error, then update your w by w plus x. And if you are at some negative point and then making error, then you do w minus x. Okay, so this is what a perceptron is. Like if it is not very clear, we can talk about it towards the end of the class, because this is a most basic principle for deep learning. You won't get much out of this course if you don't understand what a perceptron is later on. Okay. Okay. We can discuss this towards the end because I already discussed and it might not be useful for others right now. Okay. So yeah. This is last question, but a very interesting question that would give you a lot of insight about how perceptron learning works. Okay. So this perceptron, you can just read this question. So we are given 4 points in R2. Okay. So your perceptron has two inputs now. That is X1, X2. Okay. And this is your X2, X3, X4. Labels are given to be -1, 1. There are 4 points that are given to you. So initial weight that is given is W naught, that is 0, 0. What is the value? Okay, what will be the value of this W when the algorithm converges? Okay. So here theta is implicitly given to be 0. Okay. So we are here not updating theta because if you look at x, then x don't have a explicit x0 that is always 1. Okay. So here implicitly in the question it is given that my theta is 0. Okay. Let's say we start with W is equal to 0, 0 and there are 4 points that is 0, 1 is label -1, x2 is -1. I'll write it cleanly, I shouldn't mess it up. Yeah, -1 comma -1 is given label 1. Okay, and there is another point that is 2, 3, 4, -5, and the labels are -1 and 1. Okay, so let's see if my W naught is 0, 1. What is my W transpose x1? W transpose x1 is 0 times 0 plus 0 times 1. This is 0, which is again greater than equal to 0. So this point is initially from a negative class. Okay, this is a negative point. And we are predicting that it is greater than 0. Okay, so we are making some error. Okay, so what should we do in this situation? We should update the W. So my W naught becomes okay, so my W naughts become 0, 0 minus x because it was a negative point making an error, so W would be W minus x. Okay, so yeah, so this is x1, so this is 0, 0 minus 0, 1, that is 0, minus 1. Okay, now let's look at the second point. So if we take now W transpose x2, this is 0, 0 into -1 is 0, -1 into -1 is 1. So this is greater than 0 and it is a positive point, so my prediction is correct. I need not do anything over here. Now W transpose comma x3, this is 2 multiplied by 0 is 0, 3 multiplied by -1 is -3, which is strictly less than 0 and it is a negative label point, so this is also correct. Now W transpose comma x4 is 5. 0 into 4 is 0 and -5 into -1 is 5. So this is greater than equal to 0. This prediction is also correct. Okay. Now we will again check for x1. Okay. So W transpose x1 is -1, which is strictly less than 0. So this prediction is correct. So I tried solving it initially also, the options don't match from here, but the correct answer is that yeah. So the correct answer is that the value of W naught will be 0 comma minus 1. Okay. So here is another very similar question to what we did. Okay, can you please be slightly more? So what we need to do is, for every point, we'll start with some W naught that we had. Okay. So where is that thing? Yeah, update condition. Yeah. So we'll start with every point and we will see whether my W transpose X is satisfying the label from which it belongs or not. Okay. If it belongs, then we'll skip that point. If it does not, then we'll update based on these conditions. So if it is a positive point, then we'll do W plus X. If it is a negative point, then we'll do W minus X. Okay, now let's get back to the example. So initially we were asked that we are given that W naught is 0 comma 0. Okay. So when we tested W transpose with our first point, W transpose X, so 0 comma 0 would give 0. Okay, which is greater than equal to 0. So we are making an error because x1 is labeled minus 1 originally, but our model or our perceptron is saying that it should be plus 1 label. So we are making an error over here. That's why we will update our W. So as I showed you above, that if my x is negative, then I'll do W is equal to W minus X. Okay. So I am doing my W to be W minus X. So 0 comma 0 minus 0 comma 1 is 0 comma minus 1. Okay. Now I have obtained a new W. I'll do the same thing with this new W for other points also. So when I checked W transpose X2, this came out to be 1, and this was also from class 1. So this criteria was satisfied. So that's why I didn't made any change in W. And same thing happened subsequently too. Okay. So that's why my W naught was 0 comma minus 1. There is one more very similar question. I want you guys to try. I'll give you 4-5 minutes. I'm not sure whether any option matches over here or not, but you guys can give a try. There is a slight change in this question. So labels are different over here. So this is 1 1 minus 1 1 compared to minus 1 minus 1 over there. So you guys can tell me what would be the value of W naught after 2 updates, if 2 update is possible. You guys can take 5 minutes and answer me this. I'm also thinking about it. You guys also can answer me. I think it will converge after one update only, but you just need to see where it converges. And option will match is what I think. If anybody gets the answer, you can type so that others can also verify. I'll wait till 7:36, then I'll start solving. I'll write the update condition also. So if my x belongs to P and W transpose x is strictly less than 0, then you should update your W as W plus x. So P over here means that your label that is given is 1. Okay. And if my x belongs to negative and W transpose x is greater than equal to 0, then you should make your W to be W minus x. Now I think it would be more helpful for you.
Excuse me, sir.
Yes.
Yeah, can we get the recording of this session? Actually, I joined late, could
Yes,
not
so
attend.
a recording would be available in 2-3 days. So this is the first week, so I think NPTEL team will take 2-3 days time to compile the recording and everything. So if
Okay,
it will
recording
take,
is being done.
recording is being done, and from next
Okay,
week onwards, like you will get recording within half an hour or so. So I think a
okay.
Google Sheet link will be shared with you guys on NPTEL or the swayam portal.
All right.
You can use that to access all the recordings as well as
Okay,
whatever else
fine.
scripting. Yeah. Okay. So I'll start. Okay. So my W node is given to be 0, 0, right? And my x1 is 0, minus 1, and y1 for this is 1. So my x over here, x1 belongs to positive class. Okay. Now I'll take W transpose x1. So I don't think you might have an doubt in this W transpose x1, but this W transpose x1 is nothing but summation of W node 1 x1 1 plus W node 1 W node 2 x1 2, right? Yeah, that is correct. Okay, so this is what W transpose x means. So this is 0 times 0, first component of W multiplied by first component of x1 plus second component of W naught multiplied by second component of x1. This is what W transpose x means. 0, minus 1. This is 0, right? Which is greater than equal to 0, right? So because my x was from P and this condition is not satisfied, so my W transpose x is greater than equal to 0. And here we had W transpose x is less than 0. So we need not make any change. We will just continue with the current W naught that we have. Okay. Now my x2 is minus 1, minus 1, right? And the label given is again 1. So x belongs to P. Again my W transpose x is 0 because my W is 0, right now. Everything is 0 in W. Okay. This is again greater than equal to 0. So again this particular condition was not satisfied for me, so I will not change my W. So my W will stay as it is. Okay. Now my x3 is 2, 3, and the label for x3 given is minus 1 over here. Okay. So now my x belongs to negative. Now W transpose x3 is again 0. Now if you look at the condition, like if my x was from negative and W transpose x is greater than equal to 0, then I should change my W to W minus x. Okay. So because this is greater than equal to 0, so new W is W naught minus x. X is 2, 3 over here. So this becomes 0, 0, minus 2, 3, which is minus 2, minus 3. Okay. This is one update step that we have right now. Okay. So again we'll check for x4. x4 is 4, minus 5 and the label is 1. 4, minus 5 and the label is 1. So x belongs to P. Now if we take W transpose X, what it is? This is minus 2 times 4 plus minus 5 times minus 3. This is minus 8 plus 15, that is 7, which is greater than equal to 0. So for positive point, because it is greater than equal to 0, we need not do anything, we'll continue. Okay. So now because we have changed our W, so we need to revisit for x1, x2 and x3. Okay. Now for x1 again, W transpose X would look something like 0, minus 2 plus minus 1 into minus 3, and this is 3, which is greater than equal to 0, and this x1 was positive point. So this particular W satisfies for this x1, so we need not do anything. Okay. Now for x2, this is minus 1, minus 1. So W transpose of this would be 2 plus 3, that is 5, which is again greater than equal to 0. So we again need not do anything over here also. Now for x3, if we come, so for x3 we have W transpose x3 as 2 into minus 2 plus 3 into minus 3. This is minus 4 minus 9, that is minus 30, which is strictly less than 0. Now because my x3 was a negative point and the value I obtained is less than 0, I need not do anything over here also. So only after one update we converged, because we are making correct prediction on all the data points that were available to us. Okay. So again, whoever asked about convergence, this is what convergence means with the help of example. Om Prakash. Okay. Okay. So this is how perceptron algorithm works. Okay. So I think whoever asked like how do we learn theta or how do we learn W? We learn theta and W via these kind of update condition. Like at least in perceptron algorithm, these days these techniques are not used in practice, but these are backbone of a deep learning model. That's why we learned about this. These days you will have some loss function that you will define with the help on top of your multi-layer perceptron, and you try to minimize that particular loss function. Okay. And that is done via gradient descent or any other advanced method that you have. Mostly it is done via gradient descent. Okay.
Yes, sir, I have understood.
Okay. Okay. Any doubt? So this is what I had prepared for today. Any doubt? Then somebody asked about perceptron, what perceptron means. If nobody has doubt, then we can stop the recording. And yeah, somebody raised their hand.
Yeah, sir, we started with X1. Is it also, will we get the same result if we start with X4 and calculate the weights?
It is not necessary, right? You can get different weight also. You can take different number of steps also. Because in the question we were given to start from X1 and go in that order. That's why we did. But it is not necessary that you start from here. In practice, it is picked randomly and then based on that it is updated. If you would
Means
have,
we can get different result if we start with any other X.
yeah, in this example you won't get, because I can see that in this example you won't get, but there can be examples possible where you can get different your boundary, sorry, this linear separator, and also you can get sorry, you can take different number of steps to reach there. That is also possible.
Okay, fine. Thank you.
Okay. I'll take class in the same time. Yeah, Tuesday 6 to 8. But one thing that I want to make very clear, that these are more of doubt clearing sessions. I just solve questions over here, and the content covered in NPTEL lectures are much more well organized and better than what I'm covering over here.